Up until now with electrolysis, we've been looking at electrolysis as a chemical reaction that splits apart compounds, ionic compounds, into their constituent elements. It decomposes the compounds. And that works because the electrodes we've used are inert. In other words, they don't get involved in the reaction. The electrodes we've used have been carbon, and carbon doesn't get involved in the electrolytic process. What we've got here today is electrolysis, but this time we're using electrodes that are made from copper, in this case copper, and it's going to be the electrolytic purification of copper that we're looking at precisely. This same process, the same theory can be used for electroplating or gold plating or silver plating. We'd use a gold electrode in that case or a silver electrode. But we're looking here at the electrolytic purification of copper. And the reason we look at this is because the copper that's extracted from the earth comes from copper ore, copper oxide if you like, and it has impurities in it. So when the oxygen is chemically removed to make the copper, we end up with pure copper, but with impurities in the pure copper. So we've got a copper mixture, in other words. So it says the first couple of questions are just on the page here, just to emphasise that point. Copper is fairly low down the reactivity series. It's beneath carbon but above gold and silver. How do you expect to find copper in the earth? Well, it's low down the reactivity series but not at the bottom, so it's going to be joined to oxygen in the earth, so it's going to be found as copper oxide or copper ore. We call that copper oxide or copper ore. How do we produce the copper metal? It's fairly low down the reactivity series beneath carbon, so the answer is we're going to smelt it with carbon. That's a displacement reaction. The carbon is more reactive than the copper, so it takes the oxygen away from the copper, leaving copper on its own. Smelt it with carbon. So when the copper's left over, at the end of that smelting with carbon, it's copper but mixed with impurities. Now down here we've got a couple of fairly small diagrams, but we've got a beaker with an electrolyte in it, and we've got one of the electrodes is the impure copper. There is the impure copper, and it's copper, and it's got you can see the impurities in the diagram there, the dots in that lump of copper. So that lump of copper has come after we've smelted the copper oxide with carbon. Our other electrode will be very thin to start with, very thin, and we make that from pure copper. All right, now the electrolytes down here, this is going to be a solution of copper ions. A solution of copper ions, something like copper sulfate, e.g. Copper sulfate. So that's going to be Cu2 plus ions, and sulfate ions, SO4, 2 minus. Now we're not interested in the sulfate ions today. These do not get involved in this reaction. We're only interested in the copper ions. So I've written a solution of copper ions there, and I'm going to put lots of Cu2 plus ions in here. Okay, there are sulfate ions as well, but I'm not going to write those down because they do not get involved in this reaction. So the next thing we have to do, and it's very important with this process, is decide which electrode is which, because the aim of this process is to get pure copper over on this electrode and get rid of the impure copper from this electrode and get the impurities out of it. So the aim of the process is to make pure copper. So we've got impure copper, we want to make pure copper. So we have to decide which is the anode, which is the cathode. With this electrode over here, where we're going to make the pure copper, we're going to need to attract these copper ions to it. These are positive copper ions, so that needs to be the negative electrode. Therefore, that electrode is the positive electrode. So we can label that cathode and label that anode. Now, normally with electrolysis, the positive ion is attracted to the negative electrode, and that's exactly the case here. We turn the current on, and that copper ion is attracted there. And normally in electrolysis, when the ion touches the electrode, it turns back into the element. And again, that's exactly what happens here. The copper ion touches that electrode, there it is there, and it's going to plate itself onto there as a copper atom. Okay, so the copper ion turns into a copper atom. And that's exactly the same with that one there, and plate onto there, there's another copper atom. So what happens as these ions touch this electrode and plate on them, this electrode gets steadily thicker and steadily heavier as all these copper ions go over here and plate on and form copper. And that's exactly as the case in normal standard electrolysis. However, this next bit is where things start to get different. Normally in electrolysis now, because this would be a solution of copper ions, Cu2 plus aqueous, you'd have the hydroxide and the sulfate ions deciding which one was going to head towards the anode. The hydroxide would win if that were the case, but this is not normal electrolysis. We do not have inert electrodes here. We have electrodes made from metal, and they get involved in the reaction. So what we have here is lots of copper atoms mixed with these impurities. Now this copper atom says, for reasons we won't go into too much, I don't want to be the anode, the positive electrode. All of these copper ions are going over to this cathode, so what I want to do is be following them in that direction as well. So this copper ion, the way it does that, this copper atom, the way it does that, is it dissolves. It goes from being a solid copper metal atom here, it dissolves into solution and becomes a Cu2 plus ion, Cu2 plus. And the same with that one there, it goes into solution and makes Cu2 plus. Okay, so the atoms become ions. When they're atoms, they're the solid metal. When they're ions, they're the ions in solution. And when the Cu2 plus ions are in solution, guess what? They're attracted to the negative electrode and place over on that side. So that was the before diagram. Over here we've got the after diagram. So we can now see the electrode here. The pure copper electrode's gone from thin to being thick because all those ions have now plated on it, so it's thickened up. This electrode over here has thinned down because all the copper atoms have dissolved off. Okay, now the impurities, those dots, look, they're down here now because they've simply fallen to the bottom. As the copper atoms dissolve around them, then the impurities there's nothing holding them there anymore, simply drop down, gravity takes them, they drop down to the bottom of the beaker there. You may think, well, they can just be shoveled out and put in the bin because they're impurities and rubbish, but you often find precious metals in here. Platinum, gold, things like that. Precious metals can be found in those impurities. So they're not rubbish, but we do not want them in the copper. We want pure copper for making wiring and things like that. Okay, so that's what happens. Let's have a look down here. Some of these questions now. I think we've got all these labels on, haven't we? So what is the electrolyte? Copper sulfate, aqueous. Remember that it's Cu2 plus ions and SO4 2 minus ions, but the sulfate ions don't get involved, so I haven't labelled them on the diagram previously. What happens to the impurities? They drop to the bottom. Okay, let's miss that one out in the interest of time and go straight to write equations for the reactions at the cathode and the anode. Anode, positive electrode. Well, the positive electrode, the copper metal dissolved into solution, Cu2 plus. Okay, so we need to work out whether this gains or loses electrons. If you remember, one of the ways I like to do this sometimes is just to think of an arbitrary number and a strange number, if you like, of positive charges. Let's say 4. 1, 2, 3, 4. Okay, so there's 4 there, protons in the nucleus. Say copper's got far more, 63, I think, if my memory serves me correctly. But let's just say it's got 4. So here it has no charge, so it must have 4 electrons on the outside. If it had 4 protons, it has more than 4, but let's just say it has 4. Okay, over here, it's got a 2 positive charge. The copper ion has 2 positive charges. Now, the number of protons in the nucleus never changes, so there must be 4 again. If I had 4 to start with, there has to be 4 to finish with. And over here, I've got 2 positive charges, so I've got 1, 2 electrons there. I say, so hopefully we can see now, when we were here, we've got 4 electrons. And when we've got here, we've got 2 electrons. So from getting to there, we've lost 2 electrons. So if we're losing 2 electrons, they're products. So we can write them there. So that'll be our other 2 electrons. So that is that equation finished. And we can put state symbols on if we want. Copper, solid. It was a solid when it was here. And it then goes into solution, becomes aqueous. So we can write AQ there. The cathode equation. Cathode, negative electrode. What we've got here, we've got a copper ion going to it and turning into copper metal. So the copper ion was Cu2 plus, goes to the electrode, turns into copper metal, Cu. And again, we can do our positive and negatives to help us. So let's just think of a different number of positives this time. Let's do 5. Okay, so let's put 5 positives down. I'll do that at the bottom here. Maybe if I do it at the bottom down there, you can see it. 1, 2, 3, 4, 5. I just thought 5. I said it's a completely arbitrary number. It doesn't matter. 2 positive charges. So if that's the case, there must be 3 electrons balancing out. Okay, leaving those 2 positives there. On the right-hand side, copper over here. If I had 5 positives before, it has to have 5 again. The number of protons in the nucleus never changes in chemical reactions. Never changes. Okay, copper, 5 protons. And it's neutral over here. It's got no charge. It's the element. Elements are always neutrally charged, like so. So how do we get from there to there? Well, we had to gain 2 electrons. Gain 2 electrons. There we go. So we put state symbols in, solid and aqueous. And next question about oxidation and reduction. Remember, oil rig. Oil rig, oxidation is loss of electrons, reduction is gain of electrons. I always think reduction is easier to spot. Reduction is gain of electrons. Copper 2 plus ions, gain 2 electrons. The copper 2 plus here is being reduced. The Cu2 plus ion is being reduced, the copper ion. Okay, so what's being oxidized? Oxidation is loss of electrons. Well, the copper metal was losing electrons, wasn't it? That's what we had there, and that's what lost electrons. So the Cu solid, the copper metal, was losing electrons there. And there is the electrolytic purification of copper.